So we're going to take a look at displacement, and displacement is a change in the position of an object. And when we look at this change, we have to look at a final position and an initial position. And displacement is a little different than the term distance that we use. A distance only includes how far something has gone, and it doesn't consider direction at all. And distance, it makes distance a scalar because it has no direction to it. It just has a magnitude, how far it's gone. But displacement, on the other hand, has both magnitude and direction. And so what we're going to be doing is we're using a Greek symbol delta, and it means change in position. And let's look here on this slide, and you can see the change in x is defined as the final position minus the initial position. So it's going to be a mantra this year. You're going to chant, change equals final minus initial. Delta equals final minus initial. So change in anything is going to be final minus initial, or we're going to be using this all year long. So you're definitely going to get a lot of practice with it throughout the year, and you might as well get started here learning how we use it. So anyways, if we want to know Sam's displacement, which in this case is going to be defined as delta x, the final minus the initial position, you can see here his final position is 150 feet, and then his initial position was 50 feet. So you're like, okay, I could do this. 150 feet minus 50 feet gives me a displacement of 100 feet, a positive 100 feet, because in this class we've defined the positive x direction as heading to the right on our Cartesian coordinate system, and direction matters for displacement, so the positive sign matters, and indeed you can see Sam is moving to the right. So in here, let's go ahead and get to it. So the Greek symbol delta means a change in whatever. We could put anything we want in there. And it could be volume, it could be speed, it could be displacement as far as meters are concerned. It could be changes in pressure. So many different ways we could use delta, but it always means final minus initial. So when you see delta D, let's say for distance, the final distance minus the initial distance is 3 meters. Now that doesn't, it's not a vector, it has no direction, it is just a magnitude, 3 meters. We're not really sure what direction it was in, and we don't care. But the next one is very similar to the slide you just saw. Delta x equals final position minus initial position in the horizontal direction. And I made up a little problem here on the bottom. You can see I have a line, and the position started at 5 meters, the object, and then it finished at a negative 5 meters. So the final, the x sub f, is negative 5 minus the initial position, which was 5 meters. So the final answer is negative 10 meters. And this indicates that the object, the displacement, was negative 10 meters. So that means this object moved 10 meters to the left. Below we have a vertical one, so I've substituted y in, and I've drawn a picture. So this particular object is going from the negative 5 meter mark and heading up to the 5 meter mark. So we have 5 meters minus a negative 5 meters, which ends up being 10 meters. And it is a vector, so this object is moving in the positive y direction, exactly 10 meters. All right, so let's try Maria. Here's a practice problem for you. So you try this one yourself. You're like, I'm using final minus initial. That's right, the final minus initial. So you've been given delta x, and you've been given the initial position. Doesn't have a subscript on there, but you could go ahead and assume that's it because you're reading what they're looking for, the final position. So that's where she started. So this is what the solution looks like, and hopefully that's the same answer you came to as well. So along here, let's take a look at using our particle, our point particle, representing an object. So this is going to be two runners, runner A and runner B. They're on a track, and it says the position are shown at 1 second time intervals. Which runner is moving faster? So if each dot represents a 1 second time interval, each successive dot And you know that the distance between the dots is the distance that the runner covered. And we know that fast means how speed or velocity. So how far over how long? So meters over seconds. So how far over how long? And when you look at runner A, you'll notice that for each successive time interval that they are covering more distance. Runner A is moving faster. So let's try another one. Two runners jog along a track. Times at each position are shown. Which runner is moving faster? So this one's a little spicy. Got a little multiple choice going for you. So runner A, they're running for 10 seconds. Runner B also is running for 10 seconds. Instead of having each second marked on the dot, they've decided, let me go ahead and give you a dot for runner B at every 2 seconds, and they have it marked as such. So when you look at that, take a moment to think about what you think might be the answer for this one. You can hit pause on this, and the answer is going to be they're moving at the same speed. So at 2 seconds, runner A was at the 10-meter mark. So was runner B. So they're both running at the same speed. So this is another view of how you could write, do the dots every 2 seconds. All right, so speed is distance traveled over the time it took to travel it. And so here is, it's a ratio, and we'll be using this quite a bit. Speed is scalar in that it has a magnitude but no direction. Eventually we'll be getting to velocity. That is both having a magnitude and direction, but speed is scalar, just a magnitude. All right, so now velocity. Now we're getting to displacement. Now velocity is displacement over time, whereas speed was distance over time. Distance and speed are scalar. They have magnitude only. And when we get into velocity and displacement, now these are using vectors, which we usually use more than scalars. This is how you find it. Delta x over delta t. And using our mantra, x sub f minus x sub I divided by t sub f minus t sub I. Because remember, delta means final minus initial. Final minus initial. So if you stick with that and you remember that and use that while you're solving the problems, it'll help a lot. All right, so let's look at this problem here. I'm going to go ahead and solve it on the next slide for you. So if you want to hit pause and do it yourself, that would be terrific. And here's the answer. So we have final minus initial displacement over final minus initial time, and I substituted in what was given, and the final answer is -1 meters per second. Yes, Frank is moving to the left at 1 meter per second.